Pre-calculus students, welcome to your 11.4 notes, limits at infinity and limits of sequences. We're going to be studying how limits come into play as we extend to the extremes of a graph, also how that works with sequences. It connects back to some old studies of how we graph rational expressions and how we find asymptotes and things of that nature. Interesting topic, but let's go ahead and get started. Consider the graph f of x equals x plus 1 over 2x. You see I've already graphed it for you here, and you can see in blue that we have this horizontal asymptote. So if you were to find the limit of the graph as you approach positive infinity or negative infinity, you would find that it's either direction is approaching positive 1/2. Now there are a few ways you can find limits, I should say horizontal asymptotes, but this one's definitely 1/2, and we'll talk more about that in a moment. Another topic to consider is anytime you're looking at limits to infinity, you have to consider this situation. The limit as x approaches infinity of 1 over x to any power, and although I probably should say any positive power, so r greater than or equal to 1, would be equal to 0. In other words, the denominator is going to get increasingly large. 1 divided by a big number is getting close to 0. So that's what we're talking about today, kind of these two concepts. So let's get started. So let's take a look at this. If I look at number 1 here, I see that it's saying to find the limit as x approaches infinity. And by the way, that's the instructions for all these, so it's not written here. It just says to find the limit of the function. But as x approaches infinity, what's going to happen is we'll have the limit as x approaches infinity of 7 minus 4 over x squared. And yet what you have to think about is what's going to happen with 4 over x squared. Well, the larger x becomes, the smaller this becomes. 4 divided by a really big number is getting really close to 0. So we're just simply going to say it's 0. So 7 minus 0, or just simply 7, would be the limit. All right, let's take a look at number 2. It's a rational function here. F of x is equal to negative x plus 4 over 5x squared plus 2. Now, we have two different methods that we could use to address any of these problems, 2, 3, 4, and there are others as well. And I'm going to show you both on this one, knowing that you'll probably pick one that you like better and roll with it, but I want to show you both because there definitely are arguments for either of these. What I think the majority of you might choose would be a method that uses horizontal asymptotes, just like we looked at on the previous slide. So if you remember, when we have a function like this, if we want to find the horizontal asymptote, I need the degree to be the same. So I'm going to add in a 0x squared term here, and that then tells me that I have a horizontal asymptote at y equals 0 divided by 5, or just simply y equals 0. That also tells me that the limit as x approaches infinity of this function f of x is equal to 0. Okay, so again, I think that's the way most of you are going to do it, but there is another method, and I want to show it to you because I think it's possible there might be situations you prefer this, and some of you may just not love horizontal asymptotes. So the other method's kind of a funny one. You divide everything, each of the terms individually, by the largest degree variable you have. So I see here I have an x to the first, 0, 0, I have an x squared. So I'm going to divide everything by 1 over x squared, or multiply everything, I should say, by 1 over x squared. So that's going to give me negative 1 over x plus 4 over x squared divided by, well, I'd have 5, and then plus 2 over x squared. And what I have to look at then is when I start to apply the limit as x approaches infinity. So the limit as x approaches infinity of our function, and I'm not going to rewrite it all, but what happens is 1 over x becomes 0. This is what we talked about. When you have division by a really big number, it's getting very close to 0. 4 over x squared is also 0. And the denominator, 5, is just simply 5. X has no impact on that number. and then plus 2 over x squared, well, that's 0 as well. So again, we get the limit to be equal to 0. I would suggest, as I said before, that probably most of you are going to use the first method of horizontal asymptotes, but dividing by the highest degree term is actually a pretty legitimate method as well. And, it's one worth considering. Maybe you'll love it, maybe you won't. All right, so here we go. Here's the next one. Number 3, f of x is equal to negative x squared plus 4 over 5x squared plus 2. And what I notice on this one right away is that we have the same degree. It's second degree divided by second. So I know that I have a horizontal asymptote at y equals negative 1/5. And that is actually going to be the limit as x approaches infinity for our function as well. All right, so there's that one, negative 1/5. Let's look at number 4. Let's use the other method where we divide. And so I can see when I look at this that the highest degree is x to the third. So I'm going to divide each term by x cubed. And by the way, the reason we can do this is you can just think of it as multiplying by 1 over x cubed divided by 1 over x cubed. So I'm basically just multiplying everything by 1, but it's going to look obviously very different than what it did before. So I'll have negative 1 plus 4 over x cubed divided by, and we'll have 5 over x plus 2 over x cubed. Interesting. So the limit as x approaches infinity of our function f of x would be negative 1 plus 0 over 0 plus 0, and whoa, that's undefined. So what's going on here is the limit does not exist. Okay, now when we're talking about infinite limits, we really don't need to put a reason. I mean, essentially what it's saying is that it's unbound, but we're not going to worry about that. As long as you know that it doesn't exist, then you've done your job. And you could confirm this if you looked back at the original function and tried to find the horizontal asymptote. You would see we have an x cubed divided by an x squared. That means I'd have to add a 0x cubed here, and pretty quickly we'd realize there is no horizontal asymptote. This thing isn't going to be bound as we move toward infinity. As we move forward, we're going to look at sequences and how the limit as n approaches infinity affects sequences. So just think about this sequence for a minute. A sub n is equal to 1 over 3n. You can see it written out here. Now the key is this number, 1/3, 1/6, 1/9, 1/12, is getting continually smaller. So if you imagined n being a really, really large value, 1,000, a billion, 10 zillion, is that a number? I don't think so. But the larger n gets, the smaller this value gets, and therefore the closer it gets to 0. So we'd say the limit as n approaches infinity of 1 over 3n is equal to 0. Kind of makes sense, I think. So let's take a look at finding infinite limits again. And I'm going to use the division approach on this one, and then we can use asymptotes on the next one. How's that sound? Because the truth is, when I look at this in terms of which of the two methods we use or anything like that, we're treating sequences essentially the same way we treat our functions. So there's really no big change in process here. Just do what it says to do and use the same methods as what we used before. All right, so here we go. Then the limit as n approaches infinity of a sub n, well, this is going to be 4 plus 0. Denominator is going to be 1 minus 0, so that is exactly 4. All right, let's try the same idea on the next one. I'm going to use asymptotes this time, so 0n squared plus 4n plus 5, and we have a horizontal asymptote at y equals 0 over 1, or just simply y equals 0. And so that means our limit as n approaches infinity of our sequence a sub n would be exactly 0. As we move to the next slide, why don't you pause the video for a moment and try 7 and 8 on your own. So do 7 and 8 on your own. Pause the video now. Welcome back. You can see my answers on 7 and 8, and you'll notice there's not a ton of work here. The reason is I essentially just used horizontal asymptotes for both. This would be 0 divided by 12, this one's 4 divided by 1, and we're done. It really is just that simple. All right, the last one I want to go ahead and work on with you. It does have an extra complication here, and I don't think you have to make this problem super complex. But when you think about it in terms of finding horizontal asymptotes, really all you care about is the highest degree term, right? We don't care about all the other ones along the way. We care only about the highest degree. So what I'm going to do is look at the numerator. I have a 5. I have an n times 2n. That's going to give me a 10 n to the third. Now I know there are other terms there, but honestly I don't care about the other terms. I mean, if you wanted to go ahead and find them, you could, but that would be a pretty big job, and it would be honestly kind of a waste of time. The only one we care about is the first one, 5 times n times 2n. I'm underlining the terms that would give us the highest degree, okay? And the 5 is there, it's the constant. So it would look like that. All right, our denominator, well, we can do the whole denominator. That's pretty straightforward. It's 6n cubed, and you can see right away, all right, hey, same degree. So in order for us to find the horizontal asymptote, all we have to do is look at the coefficients. So the limit as n approaches infinity of this sequence a sub n is 10 over 6, or just simply 5/3. All right, folks, I hope that lesson makes sense to you. Make sure you've taken good notes and come to class ready to ask questions if you have them. Have a spectacular day.